let's use our experience with double integrals to bump things up a dimension. So suppose we have a box that occupies this rectangle from 0 to 3 in the x direction, from 0 to 4 in the y direction, and from 0 to 2 in the z direction. And suppose that at the point x, y, z, it has this density, x over z plus 1, all plus 2. It doesn't really matter what the units are, but maybe x, y, and z are in centimeters, and maybe this density is in grams, that's a g, grams per cubic centimeter, something like this. So what is the total mass of this box? Well, one thing you might be tempted to do is just take this density and multiply it by the volume of the box. But the thing is, this formula only works if the density is constant, so that every point in the box has the same density. That's when it makes sense to use a product formula like this. But that is not the case here, because the density in our situation is a function of position. So what we need to do is, what we have been doing since you learned integral calculus, which is split this problem into infinitely many, infinitely small pieces, solve the problem for one individual piece, and then do some kind of integral to put all the pieces together. So let's focus on the little speck of volume, at point x, y, z. Okay, so for this, we're going to have a coordinate system, a z-axis, an x-axis, and then the y-axis is going into the screen here, and there is some point at xyz. Near that point there's a little speck of volume. We could think of it as a little box of volume, and the volume at that point, well, it's going to be dv, but right, d of something is how we express the idea of an infinitely small chunk of that thing. So there's this infinitely small chunk of volume. Of course, because we have this box of volume, right? If we zoom in on this box of volume, we get this box of volume by moving a little bit in the x direction, so that's dx, a little bit in the y direction, that's dy, and a little bit in the z direction, that's dz. So this volume dv is actually dx, dy, dz. And we could put these in any order. Okay, so that's the volume at x, y, z. So what's the mass of the speck of material at the point x, y, z? Well, here's where we get to take advantage of the fact that we've taken an infinitely small bit of volume. For an infinitely small bit of volume, the density can't really change, because density changes as you move over some extended distance, but we're talking about infinitely small distances. So the density doesn't have time to change. So for the mass at this position, we can write that the mass is density times volume. Right? We couldn't before because we were talking about an extended volume, but this infinitely small volume isn't really extended over any sort of finite quantity or any finite distance. Okay, so what is the density at this point? Well, that's what the function tells us. That's rho of x, y, z. And what's the volume at this point? Well, that's what we call dv. Okay, so that's the mass at one single point. To find the total mass, we just need to take all of the little bits of mass and add them all together. So that's going to be some kind of integral, but what kind of integral is it? Because dv is dx times dy times dz, we need one integral for every variable. And so that's going to be not a single integral, not a double integral, but in fact a triple integral. Yes, 3 integrals, one for each coordinate. So we're going to integrate triple integral of rho of x, y, z, dx, dy, dz. And again, it seems as though we could put these differentials in any order, as long as we arrange the bounds to match the order of the differentials that we chose. So what should the order of the differential, what should the order of the bounds be? Well, look at our x, y, and z bounds up here. So x is from 0 to 3, y is from 0 to 4, z is from 0 to 2. So we just need to put these in the same order. Now let's see, z is on the outside, so 0 to 2. Y is in the middle. Y was, what was y? 0 to 4. And x was from 0 to 3. So this is what we need to calculate. Integral from 0 to 2, integral from 0 to 4, integral from 0 to 3. Our density function, which was what? X over z plus 1 plus 2. Yes. X over z plus 1 plus 2. Like this. dx, dy, dz. Okay, so we have a triple integral because we have 3 independent variables. We have 3 differentials that we can integrate against. And we wrote this triple integral as an iterated integral. All right, now we can evaluate this. I mean, just like with double integrals, evaluating an iterated triple integral is just a matter of doing the integrals one at a time. So let's do our x integral. So the integral of this mess with respect to x is 1/2 x squared over z plus 1 plus, and then the integral of 2 with respect to x is 2x. Now we need to evaluate this at 0 and at 3, and then dy dz is still waiting for us to integrate those variables. So integral from 0 to 2, integral from 0 to 4. So now let's plug in our bounds. 1/2 times x squared, x is 3, so that's 9. So let me put the 9 right here, times 1 over z plus 1, plus 2 times 3, so plus 6, minus, and then when we plug in our bottom bound, we get 0 plus 0. So nothing but zeros from our bottom bound. dy dz. Okay, so next up is our y integral. So integral from 0 to 2. Notice that this stuff that we're integrating actually doesn't have any y's in it. So we can kind of treat it all like an integral, like a constant for the y integral, and stick our y over here, and then evaluate at 0 and 4 dz. And then when we plug in our bounds, we get, let's see, 9 over 2 times 1 over z plus 1 plus 6 times, and now plug in our bounds, 4 minus 0 dz. And then finally our z integral. So let's see, 9 over 2, that's a 9, not an a. That didn't help. That just made it worse. 9, there we go. Okay, integral of 1 over z plus 1, that's natural log of z plus 1, plus 6 times z, all times this 4 on the outside, and then integrate or evaluate from 0 to 2. So now plug in our bounds. Let's see, 9 over 2, natural log of 2 plus 1 is 3, plus 6 times 2 is 12, all times 4, minus, and now let's plug in 0. We get 9 over 2, natural log of 0 plus 1, so that's 1, plus 6 times 0. Natural log of 1 is 0, so actually this whole piece is 0. And so we're just left with, let's see, distribute the 4, 18 natural log 3 plus 48. Okay, now for the units, right, our density was in grams per cubic centimeter, and we multiplied this by a volume, an infinitely small volume, dV. That's going to be in cubic centimeters, and so the centimeters, cubic centimeters cancel, and that means that this final mass is in grams, which is good because that's a mass unit. Okay. So what we did here with this example is we invented triple integrals, which are exactly like double integrals except with one more variable. Okay, so a triple integral of a function over some domain in xyz space is, we'll write it this way with 3 integral swoops, and our domain is d, and write your integrand function, and then dv. If we're using Cartesian coordinates, then dv is just dx, dy, dz. In any order, we can rearrange these. Keep in mind that this is really, as with any integral, this is really a shorthand for a limit where we evaluate, right, if we have some extended volume in 3D space, we have a bunch of points scattered throughout the volume where we evaluate the function. At each point, we multiply the value of the function by the chunk of volume near that point, add up all of those individual bits, and then we take a limit as the size of our little box of volume goes to 0, right? So technically, that's what's happening in the background. Fortunately, as with double integrals, Fubini's theorem guarantees us that as long as our integrand is continuous, I should be more specific, continuous on the region D that we are integrating over, Fubini's theorem guarantees us that we can write a triple integral as an iterated integral in any order we please. So that hopefully is reassuring. We don't have to worry about different orders giving us different results. That can happen if your function is not continuous, by the way. But for continuous functions, fortunately, we don't have to worry about that. Okay, so the upshot of that is that we can choose whatever order we consider to be nicest, right? That's the advantage of Fubini's theorem. So for example, suppose we have charge distributed through a block of insulating material so that the charge density at point xyz is given by, say, y times sine of z. What is the total charge in the region given by this box? And when I write regions this way, this is always a rectangular box where the x-coordinate, the range of x-coordinates is first, the range of y-coordinates is second, and the range of z-coordinates is third. Okay, so charge density is just like mass density in that to get the total charge, you multiply by the density. Of course, since our density is varying from point to point, we have to do all our calculations in the neighborhood of each point. So at the point xyz, the volume is dV, and so the charge at that point is rho of xyz, the density, times dV. So that's at a single point. And then the total charge, well, you just take all the little bits of charge and add them up. So integrate over that region, our density function, our charge density function, dV. Okay, I guess the units for this charge density would be something like coulombs per cubic centimeter or something like that, right? Charge units per volume unit, whatever charge and volume unit makes sense in your situation. Okay, so let's write this all out. We can choose any order we want. I don't know what order to do, so let's do, for variety, let's do things in the opposite order from last time. dx on the outside, then dy in the middle, and then dz on the inside. So our bounds are going to be -2 to 3 in the x direction, -1 to 1 in the y direction, and 0 to pi over 6 in the z direction. And our density function was, I think it was y sine z. Yes, y sine z. Y sine z. Okay. Notice that for this particular example, all of our bounds are constant, and our integrand is a product of functions, a function of x, a function of y, and a function of z. Sorry, a function of z. So we can use that separation trick, right? This was exactly the situation that let us sort of split everything up according to its own variable. And that works just as well for triple integrals as it does for double integrals. So we can write this as integral from -2 to 3 dx. And the x function in this product is, right, if there isn't one, that means there's a hidden times 1. And so the x function is just 1. So that's our x integral times integral from -1 to 1 of y dy. And then integral from 0 to pi over 6 sine z dz. Okay, this is especially nice, splitting things up in this way is especially nice in triple integrals because right, the more integrals you have stacked on top of each other, the more you would prefer to do them simultaneously instead of one after the other. So now that we have 3 integrals stacked on top of each other, doing them simultaneously is much, much better than doing them one at a time. Okay, so our x integral of 1 with respect to x is just x from -2 to 3 times integral of y with respect to y is 1/2 y squared, and then that from -1 to 1 times, and then integral of sine of z is negative cosine of z, and that's from 0 to pi over 6. Okay, now we can evaluate everything. So for our x factor, it's 3 minus -2. For our y factor, it's 1/2 times 1 squared minus -1 squared. And for our cosine factor, it's minus cosine pi over 6 minus negative cosine of 0. Don't drop a minus sign here, careful. Of course, none of this matters because this middle factor is 0. So in fact, all of this stuff adds up to 0 in the end, or multiplies out to 0 in the end. So this is the total charge. How is it possible to have a total charge that is 0 if your charge density function is not 0? How does that make sense? Well, charge, unlike mass, charge comes in positive versions and negative versions. So what's happening here is in this block of material, in this block of insulating material, in some places there are positive charges, in some places there are negative charges, and so if you add up the total, the negatives cancel the positives, right? So that's what's happening. This has to be a block of insulating material for this to happen, though, because if it's a conducting material, these charges will move around. So that's why I insisted that it be an insulating material. So if you did the integral in another order, hopefully you got the same result, 0. Because, again, that is guaranteed by Fubini's theorem as long as our integrand is continuous, and this particular integrand, y times sine of z, definitely is continuous.